I'm Dr. David Kirtley of Helion Energy. This work we presented at the American Physics Society Plasma Physics meeting this year. This is a work by primarily Dr. Sean Lewis, but also Dr. Anthony Pancati and myself on the fundamental theory of how Helion recovers magnetic energy in a thermonuclear field reverse configuration system. So starting with the basics, what is a field reverse configuration? This is a plasma physics topology that's self-organized into a closed field. And what that means is, and what you're seeing on the screen, is a cylindrical topology, a cross-section of a field reverse configuration plasma after we've made it. And it has a couple of really key unique features. The first is that this FRC in a cylindrical geometry has fully closed magnetic fields and is high beta. Beta is the ratio of the internal plasma pressure to the external magnetic pressure, and that's really key to what we're about to talk about, in that this plasma pressure, as you heat a fusion fuel inside of an FRC, like we have done in our 6 fusion prototypes, that applies a pressure inside, the particle pressure increases, but also that applies a pressure to the outside, the external magnetic pressure increases. And that's really critical because it allows the FRC to do work on that magnetic field and allows us to recover electricity directly from that electric field and that particle pressure without steam turbines. That's really the key to what Helion does. So high beta is the ratio of the external to internal magnetic pressures. Couple of other key things is that as you compress an FRC radially, as you increase the magnetic pressure such that it compresses in radius, it also pulls in axially. So there's some well-established scaling, axial length scaling for that compression. Here I'm showing work from Spencer in 1983, and there's also empirical scaling that backs this up. Of how the axial length changes. This is what we'll be using for this analysis. Also, other key parameters is the separatrix ratio, which is the location of that external field reversal of the external closed field. In this, it's RS, as well as the expansion, as well as the axial compression ratio, X, is another key parameter. So in the work we're going to be talking about, and what Helion fundamentally does with its fusion plasmas, is that we take 2 of these FRCs, we merge them into a central compression region. We then increase the magnetic pressure, compressing that FRC until it gets to a fusion temperature where it starts to burn, to increase in pressure and temperature and energy. We then expand that FRC, extracting that energy, that electricity, that magnetic energy, and that particle energy as electricity directly. Some key parameters right now, we've presented this previously, but you can very well approximate an FRC as a uniform cylinder with a given fixed radius and a fixed length. That gets within 10% of the energy content of the full magnetic and plasma profiles for an FRC. There's 2 key parameters, the compression ratio, so the volume that you initially start, in our case, post the merge, and to the peak compression, and then the expansion from that fully heated plasma to then an expanded cooled plasma as you've extracted that electricity. Those are some of the key things we're going to be talking about. The analysis we did here expands on some work that was done many years ago in 1973 that looked at how you can take a generic MHD or high beta plasma, compress, and expand it. Here we're building on this, starting with the classic, diesel cycle, remember from your thermodynamic textbooks, where you have an initial volume, you then compress a gas or a fuel, you then burn at a constant pressure. And what that means functionally is you allow the volume to increase at that constant pressure. You then have an expansion cycle where you then recover all of that much of that initial energy and that new heat energy that you added into a position 4 where you now have electricity out of the system. You have a more advanced cycle. We're going to be talking about this is the first we know of for fusion, called the Otto cycle, where you have that initial merged state. You compress that fusion fuel to an increased volume, but now as fusion happens, it increases in temperature and energy. You hold the volume. So what that means functionally for high beta plasma is it increases in pressure, increases in temperature in kT, increases in temperature, density, and pressure, increasing the fusion reaction. You can imagine how that's really good for fusion processes. You then do an expansion cycle, recovering all that energy directly as electricity. Here's the standard efficiency equations for a diesel cycle of a given compression and expansion, as well as the Otto cycle One of the key parameters here that we'll talk about is gamma, so the adiabatic index of your gas. For this analysis, we're using 1.8. We do that because the fusion plasma is a pure gas at 1.6, but the magnetic field is a gamma of 2. And so actually, because we're high beta, if you assume beta equals 1, you actually get to a nice 1.8. There's a lot more advanced derivation of this in other works. One other key thing that I'll point out is that in this analysis, we very simply take an initial volume, compress, and expand. But in a system like Helion's, you are not limited to the initial volume to your final expansion ratio. You can actually expand further, increasing the length of the fusion plasma, or maybe even into the accelerator regions of a Helion system. We call that the M parameter, which is this named the extra expansion factor. And so that becomes a pretty interesting and critical parameter as we go. So taking that, you can now derive some very high-level derivations in terms of Q. Now, there's many definitions of Q in the fusion community. I specifically mean simply the change in the internal energy relative to the starting internal energy of the fusion fuel, of the plasma itself. And then look at it, and then you can put a good equation together, which looks at the total efficiency of that system of energy in versus electricity extracted. Energy extracted, in this case, in terms of electricity. We then take this in terms of compression ratio, the fusion Q as I've defined it, gamma, as well as this extra expansion ratio, put that into the diesel cycle, and now have a full diesel cycle efficiency. This is the full equation that we derived for this. And then similarly, you can do the same thing for an Otto cycle and build that full derived equation. Now, some of the key results that we'll talk about today: diesel versus Otto efficiency. So in the diesel efficiency, what you can see is actually, and this should be expected just based off of the temperatures involved, but you can actually get to quite high efficiencies with a diesel cycle using a fusion system at high beta. And so what we see here on the left is the efficiency versus the compression ratio, and the final compressed X sub S, so that's the final compressed ratio of the separatrix to the coil ratio. So you think about that, you can think about this as in a typical compression cycle, you'd be thinking about this as a stroke of a piston. But in this case, it's more than just 1D compression, because you have both the radial and the axial compression, and a given M factor, that extra expansion factor. But what you can see here is for a typical system where you might compress an FRC down to 20 to 50% of its initial radius, you can have very easily in a diesel cycle at a Q of 1 in this system of energy efficiencies well north of 60%. That's pretty good. But even further than that, in an Otto cycle, because you do a compression, you hold it, it burns, you can actually get to much higher efficiencies. So now you can actually talk about efficiencies of electricity recovery from one of these systems well above 80%. This is very encouraging. Now, this is not the full story, because in a full compression of an FRC, you don't have, it's not as a simple idealized equation of initial volume, final volume, but you have a range of that full compression while fusion and burn has happened. We solve for that too, and you can see what happens to these curves. So this is for the diesel efficiency. Now we've gone to a lower Q operating condition. We'll talk about that in a second. But what you start with is an initial compression down to, say, 60%. You compress that FRC down to 30%, get to your peak compression, and you can integrate over that and get a total of efficiency, again, above 80% efficiencies for this type of a Helion-sized system. The last key point to this is Q, that in a diesel cycle specifically, as you are doing fusion and you're expanding that volume, that expansion process is lost volume. That's lost energy that you can't recover. So the higher the Q of the fusion reaction, the more of the fusion reactions you have, actually the lower efficiency you have for that diesel cycle. You still get more energy out, because you end up with the Q times the energy efficiency of recovery, but it's a lot less advantageous, and it enables lower Q systems to be really functional in making electricity. And in fact, this what I'm showing you now is for a Q as defined as the internal energy over the total energy of less than 1, a Q of 0.2, and still you're talking about on the order of 80% energy efficiency of recovering that internal energy. It's quite impressive. And it leads you to the next thing that you can do of advanced burn cycles. So in an Otto cycle, you might be able to do something even more complex using maybe pulse-forming networks or other things that we can do with our capacitor power systems. Or you have an adiabatic compression phase. You do this burn with maybe some small amount of volume increase, but significant energy increase. And then you do that adiabatic expansion at the end. And then a diesel cycle where maybe you now burn and hold for a while and then do the expansion. And so you can see what that advanced cycle would look like. And then a simple, very simple system of just do a compression, do an expansion. So what we call the sinusoidal diesel equation. So some of the other key things that we found in this analysis that really helps us guide where we go build generators in the future. This extra expansion factor, the higher M, the closer you can get to this idealized equation, which means we're going to utilize all of the magnetic coils and all of the magnetic geometry for an FRC. That's something we believe we can do in a Helion system where you have this axial topology. And then really optimizes for Otto cycle for very fast fusion where you do a fast compression, high field burn, and then an expansion. And then diesel cycle if you want to lower the size of maybe your capacitor bank and go to longer timelines and longer operation. Thank you very much.